Okay, so today we're going to finish up statistics with a section 8.8, talking scatter plots, correlation, and regression lines. So here we have a scatter plot. One of the most powerful tools statistics gives us is the ability to explore relationships between two data sets containing quantitative values, and then use that relationship to make predictions. For example, a student who wants to know how well they can expect to score on an upcoming final exam may consider reviewing the data on midterm and final exam scores for students who have previously taken the class. It seems reasonable to expect that there is a relationship between those two data sets. If a student did well on the midterm, they were probably more likely to do well on the final than the average student. Similarly, if a student did poorly on the midterm, they probably also did poorly on the final exam. Of course, that relationship isn't set in stone. Your midterm exam score doesn't cement your performance on the final. You might use that poor result to buckle down and do better on the final. The statistical method of regression can find a formula that does the best job of predicting a score on the final exam based on a student's score on the midterm, as well as give a measure of the confidence of that prediction. In this section, we'll discuss how to use regression to make these predictions. So first, let's look at how this works. So we're looking at a relationship between quantitative data sets. Now, before we evaluate a relationship between two data sets, we must first decide if we feel that one might depend on the other. In our example above, it's appropriate to say that the score on the final depends on the score on the midterm, rather than the other way around. So it's worth noting that not every pair of related data set has clear dependence. For example, consider the percentage of the country's budget devoted to military and a percent earmarked for public health. These data sets are generally related as one goes up, the other goes down. However, in this case, there's not a preferred choice for dependence, as each could be seen as depending on the other. When exploring the relationship between two data sets, if one set seems to depend on the other, we say that that data set contains values of the response variable or dependent variable. This variable depends on what the other one is, thus dependent. Data set that the response variable depends on contains values we call the explanatory variable or independent variable. It's not dependent on the other. So let's look at some pairs of data sets and identify which would be the best choice for the response variable, the dependent variable. A person's age and their annual income. Well, the older you get, you tend to make more income to a degree. So that's probably what they're looking for, annual income. But think about this. Once you get to retirement age, depending, your annual income may drop down if you didn't save money some other way. Also, we can look at this from another standpoint too. If you have a high annual income all your life, you may be able to provide yourself with more medical care that would extend your lifetime. But again, we're going with annual income. That seems the most obvious. What about a student's GPA and their score on the SAT? Now, what do you think? A higher GPA give you better SAT score? Possibly. Higher GPA tends to mean you're better at classes. So we'll go with the SAT being the response variable. Excuse me. Okay. A student's GPA and the number of hours they spend studying per week. So does the GPA affect your hours you study, or do your hours you study affect your GPA? We're going with the other way, so the GPA in this case would be the response variable. Once we've assigned roles to our two data sets, we can take the first step in visualizing the relationship, creating a scatter plot. Scatter plot is a visualization of the relationship between two quantitative sets of data. Scatter plot is created by turning the data sets into ordered pairs. First coordinate contains the values from the explanatory data set. Second coordinate contains the corresponding data values with the response data set. These ordered pairs are then plotting in the XY plane. So this is going to get a little messy. So we're going to look at creating a scatter plot to visualize the following data, showing the top 5 NFL receivers by number of receptions for the 2019. Treat yards as the response. So we're going to take our XY plane. We're going to have receptions down here and yards over here. And we're going to do one of them cardinal sins. And I'm going to start at 1100 and go up by hundreds for spacing reasons. 14, 15. And then I'm going to start 100, 105, 110, 115, 120, 125, 120, or 130. Okay, so our first person had 127 receptions and 1535 yards, which is going to be about there. Next up, we had 115 and 1374, which would be about there. Then we had 115 and 1407, which would be a little more than that. Then we had 107 and 1196. Then we had 105 and 1416. Okay, so there's our scatter plot. When we talk about plotting one set versus another, the first is the response and the second is the explanatory. So what about reading these scatter plots? They give us information about the existence and the strength of a relationship between two data sets. To break information down, there are a series of questions we might ask to help us. First, is there a curved pattern in the data? If so, we can stop. None of the linear regression techniques from here to the end of the section are appropriate. So we're not going into other regression techniques. There are others out there, though. Once we've confirmed that there is no curved pattern in our data, we can move to the next question. Is there a linear relationship to this? To answer this, we must look at different values of explanatory variable and determine whether the corresponding response values are different on average. It's important to look at the values on average because in general, scatter plots won't include just one corresponding response point for each value. As you saw, well, we had 107 and 105. No, we did have two 115s, and we had two different values. So let's look at our figure below, and we highlighted points whose x values are around 50 and around 80. Notice there's several of them in there. All right. Not too far, didn't I? Yep. So now we can estimate the middle of each group of points, and we'll add our estimated average to the plot. Okay, so you can see here we have our little red X's or red stars or asterisks. Since these two starred points occur at different heights, we can conclude that there's likely a relationship with worth exploring. Then we look at positive and negative linear relationships. Another way to assess whether there is a relationship between two data sets in a scatter plot is to see if the points seem to be clustered around a line, specifically a line that's not horizontal. The stronger the clustering around that line is, the stronger the relationship. Once we've established that there's a relationship worth exploring, it's time to start quantifying that relationship. Two data sets have a positive linear relationship if the values of response tend to increase on average as the values of the explanatory variable increase. The values of the response decrease with increasing values of the explanatory variable, then there is a negative linear relationship between the two data sets. The strength of the relationship is determined by how closely the scatter plot follows a single straight line. The closer the points are to the line, the stronger the relationship. So let's look at some examples. Here, this one looks beautiful, right? Perfect negative relationship. Note as our horizontal variable increases, our vertical variable decreases. So it's perfectly aligned and it's negative. Here, on the other hand, not so perfect, but there's probably a line we can use somewhere along this way. And again, it's all pretty close to that line. So that would be a strong negative relationship. Okay, here is kind of a mess. So you can kind of see something that might go like that. So we have a negative relationship maybe, but everything, stuff is too far away. So it's very weak. And of course here, there's no relationship at all. The strength and direction, positive or negative, of a linear relationship can also be measured with a statistic called the correlation coefficient, denoted by a small r. Positive values of r indicate positive relationship, while negative values of r indicate a negative relationship. Values of r close to 0 indicate a weak relationship, while values close to positive or negative 1 correspond to very strong relationships. So there's no firm rule for a cutoff between weak and strong. We typically think of 0.7 plus or minus. So if R is between negative 0.7 and positive 0.7, we consider that a weak relationship. So let's look at here. Come on, cooperate, computer. So for each of the plots below, answer the following questions. Is there a curved pattern to the data? And we're talking this first one here. And no, there is not. Take a guess at the value of R. Well, it's going to be negative. And what do you think? If we put a line down the middle, they're all pretty close. So I would say strong. Okay. Here we have a curve. So yes, which means we stop. And here we have, can we even say that's positive or negative really? I could go with no correlation or very weak correlation, if any at all. Now, finding accurate correlation coefficient is frequently done using technology, which is, of course, beyond our scope. We're not going into technology. But there is a way to find, or there is something called linear regression. This is the final step in our analysis of the relationship between two data sets to find and use the equation of a regression line. We're given a set of explanatory and response data. The regression line, also called least squares line or line of best fit, is the line that does the best job of approximating the data. What does it mean to say that a particular line does the best job of approximating data? The way that statisticians characterize this best line is rather technical, but we'll include it for the sake of satisfying your curiosity and backing up the claim of best. Imagine drawing a line that looks like it does a pretty good job of approximating the data. Most of the points in the scatter plot will probably not fall exactly on the line. The distance above or below the line a given point falls is called the point's residual. We would compute the residuals for every point in the scatter plot. If you take all those residuals and square them, then add the results together, you get a statistic called the sum of squared errors for the line. The name tells you what it is, a sum, because we're adding squared, and because we're squaring, an error is another word for residuals. The line that we choose to be best is the one that has the smallest possible sum of squared errors. The implied minimization smallest is where the least in these squares come from. Squares come from the fact that we're minimizing the sum of squared errors. So, finding an equation of a regression line. How do we do this? Recall the point slope form equation of a line. If a line has a slope m and passes through a point x0, y0, then a point slope form of the equation of the line is y equals m times x minus x0 plus y0. So a regression line has two properties that we can use to find its equation. First, it always passes through the point of the means. So if the mean of the x and the mean of the y are the means of explanatory and response data sets respectively, then the point of means is x bar y bar. We can use that as a point in the point slope form of an equation. Second, if s sub x and s sub y are the standard deviations of the explanatory and the response data sets respectively, and if r is the correlation coefficient, then the slope is m equals r times s sub y over s sub x. Putting all that together with the point slope formula gives us this. Suppose x and y are explanatory and response data sets that have a linear relationship. If their means are x bar and y bar respectively, their standard deviations are s sub x and s sub y respectively, and their correlation coefficient is r, then the equation for the regression line is y equals r times f sub y over s sub x times x minus x bar plus y bar. So suppose you have data sets x and y with the following statistics. S has a mean of 100, so x bar equals 100. And a standard deviation of 5, so s sub x equals 5. Y has a mean of 200, so y bar equals 200. And a standard deviation of 20, so s sub y equals 20. And their correlation coefficient is 0.75. What's the question? What's the equation of the regression line? So my equation is y equals r times s sub y over s sub x times x minus x bar plus y bar. So let's fill in the values we have. Y bar. So y equals r, 0.75 times standard deviation of y, 20, with a standard deviation of x, 5, times x minus x bar, which is 100, plus y bar, which is 200. So we'll do a little PEMDAS here. We get 0.75, 20 divided by 5 is 4, times x minus 100 plus 200. 0.75 times 4 is 3, times x minus 100 plus 200. Distributing, we get equals 3x minus 300 plus 200. Combining our like terms, we have 3x minus 100. So our regression line is y equals 3x minus 100. Okay, we can also use the equation of a regression line. Once you've found the equation, what do we do with it? Well, we look at two possible applications, making predictions and interpreting the slope. You can use the equation of the regression line to predict the response value for a given explanatory value x. All we do is plug in the explanatory value into the formula and see what values result. This is useful in two ways. First, it can be used to make a guess about an unknown data value, like one that hasn't been observed yet. Second, it can be used to evaluate performance, meaning we can predict an outcome given a particular event. The second application of the equation of the regression line is interpreting the slope of the line to describe the relationship between the explanatory and response data set. So, given our regression line, y equals 0.884x minus 456, where y is the number of runs scored and x is the number of hits. Answer the following. How many runs would we expect a team to score if they got 1,500 hits? So we take y equals 0.884 times x, which is 1,500, minus 456. So we have 0.884 times 1,500. That worked out nicely. Gives me 1,326 minus 456. And we would have 870 runs. Okay. So the Kansas City Royals scored 691 runs from 356 hits. Did they overperform or underperform in terms of runs scored based on hit total? And by how much? Well, let's see. Let me do this. Make a little more room here. That might be enough. So our equation says run scored. We have 691 equals 0.884 times hits, 1356 minus 456. Actually, we'll leave this as y. We know what it is, but we want to see what they should have scored, and then we'll compare it to what they did score. So 0.884 times 1056, and we get 1198.704 minus 456. Subtract our 456 and we get 742.704. That's what they should have scored, but they only scored 691, so they underperformed. They didn't score as many as would be predicted here, and the difference would be 51.704. So, what does the slope mean in this regression line? Well, looking at the regression line, if you remember, the slope is this right here. So what happens? What does this do? For every hit gained, the number of runs increases by 0.884. So we could write something like number of runs increases by 0.884 or every additional hit. That brings us to very common misuse of regression, which involves making a prediction about something that doesn't belong in the data set. So here's the biggie. Correlation does not imply causation. Just because you can create a regression line doesn't mean that it's accurate. One of our most common fallacies about statistics has to do with the relationship between two data sets. And again, this is referencing some of the stuff that's in the text that we don't have, or that's in the online version of the text, which we're not referring to. But in this data set that they have, they found that the correlation coefficient between the 75th percentile math score and the 75th percentile verbal SAT scores is 92%. So that looks pretty strong in a positive direction. The slope of the regression line that predicts the verbal score from the math score is 0.729, which might interpret as the 75th percentile math score goes up by 10 points. We'd expect the corresponding verbal score to go up by 7 points, right? 72, 70%. Does the increase in the math score cause the increase in the verbal score? Probably not. What's really going on, of course, is the third variable that's affecting both. To raise an SAT math score by 10 points, a school would recruit students who do better on the SAT in general. These students will also naturally have higher SAT verbal scores. This third variable is sometimes called a lurking variable or a confounding variable. Unless all possible lurking variables are ruled out, we cannot conclude that one thing causes another. So correlation does not mean causation. Very big to remember. That's something that is frequently forgotten. And that finishes up this section as well as this chapter.